In this second part, we will first take a deeper look into what's happening in a plasma itself, and then we will see what determines absorption, how the absorption mechanism works, and what the consequence of that is for laser materials processing. So if we look detailed what's happening in a plasma, it depends very much on the vicinity of the next charges to a test charge. Here you can see a test charge as we put it somewhere in space, and now this charge has a certain potential which is plotted below. This is a typical 1/r dependence of the potential. If we now add further charges and look at what is happening to the charge, the test charge itself, we will have a change of that potential, because in this case the positive charge will attract the electrons and it will repel the ions. As a result of the presence of the surrounding charges, the potential of course changes. In this example here, the change is not very much. You see the blue line is very close to the red one, but that can be different depending on the conditions. On the left you see the equation to the potential, which is simply the exponential dependency of the distance of the charges as we know it, and from that we can deduct and calculate what is called the Debye length, which is a characteristic value which separates two regimes, as you see again on the right hand side, where the distance of the charge is plotted over a normalized distance, normalized by the Debye length lambda d, and for distances below lambda d we'll have the individual influence of the charges, and for distances larger than lambda d we will have practically no influence of the surrounding charges. As a further point in this plasma session, I would like to make a little excursion on the definition of a plasma, because just charged particles are not really a plasma. It is a matter of shielding, and there is a shielding radius which is called the Debye radius. This Debye length is plotted here in this graph on the lower left. You can see the Debye screening length as a function of the carrier density, and you see the higher the density gets, the smaller the Debye length gets. And the reason for this is that if we are beyond the Debye length, then this plasma looks kind of uniform. If we are in the other domain, the plasma looks like individual charges, and we have to take into account each individual contribution of an individual charge. So this is the meaning of the Debye length. It separates, so to say, if a test particle, a test charge, sees a homogeneous uniform plasma with net zero charge, or if it is in the plasma, if the scale is such that it is in the plasma and sees the individual charges. More details in a second. Just as a very simple example, if you take this air here in classical normal conditions, room temperature, we do have electrical charges, because due to the background radiation, the universal background radiation, we have gamma rays which ionize the air permanently, and the number of electrons per centimeters cubed right here is somewhere between 100 and 1000. This is not very much, but it is the equilibrium number of charges that we have under normal conditions in air in this atmosphere. So if we take these values and you look at the ionization by the cosmic rays at electron density of about 1000 per centimeter cubed, at room temperature the Debye length would calculate to 38 kilometers. In other words, it is not really a plasma, not a homogeneous distribution of charges. The charges are so close to each other that we can identify their individual contribution. Coming to an explanation of the absorption, I would like to show you two slides on inverse Bremsstrahlung. That is the terminus technicus for this process of absorption in a plasma. And if you again imagine the electron bouncing up and down in the electric field as shown in the upper curve, you understand and remember that it cannot pick up any energy in the time average. However, because it just accumulates and loses the energy as shown in the lower view graph. But however, if we allow collisions and take the ideal situation that right at the maximum speed of the electron, it would collide 180 degree elastically with an ion or an atom, changes its direction. In this instant, the direction of the electric field changes, and corresponding to this change of the direction of the field, again, the electron now is not stopped, but it is accelerated further because now it is in phase with the field. And after half a period, imagine the same thing happening again. We would have another collision and again an increase of energy of the electron and so on. Of course, this is an ideal picture, but in reality, we understand in this model that due to the collisions, the phases change, the directions of the electrons change, and therefore they can accumulate energy in this plasma. This is what we then describe phenomenologically just by this collision frequency ν_c. So, as a consequence of all that, for materials processing, laser light can be absorbed in plasmas or it cannot be absorbed in plasmas depending on the number of electrons, the electron density in that plasma. Starting with the lower picture, the so-called process regime, you see a plasma on the surface in the beginning of a drill. If you look carefully, you can see that the drilling depth here increases from picture to picture. The time frame from one picture to the next is something like 50 nanoseconds. So it's a real high-speed resolved set of photos. And in the process regime, we do have a plasma. The plasma does absorb a certain amount of laser energy, but it does that in a way that the energy is transferred to the surface quite homogeneously. In the upper position, in the upper picture, you see a different case at higher intensities. If you use CO2 radiation and increase the intensity over 10 to the 7, about 2 times 10 to the 7 watts per centimeter square, we get an absorption in the plasma which ultimately leads to a dispatching of the plasma, a detaching of the surface. It just moves off the surface and absorbs practically all the energy in this plasma, and practically no energy will come to the surface. Of course, this is a mode which we like to omit, which we do not want in material processing. So for welding and cutting applications, we stay under the critical value of 2 times 10 to the 7 watt per centimeter square. To demonstrate that, take a look at this video here. You will see a plasma on a surface here already visible. And the intensity now is chosen just at the threshold. So what you see is sometimes the plasma stays at the surface, but sometimes it will just move off the surface towards the laser. So now that the video is running, you can see the plasma and sometimes it just detaches and it moves towards the laser, and then it diminishes and the process starts over again. So from the physics point of view, we differentiate the two cases of the plasma on the surface and the detaching plasma as laser-supported combustion. Combustion is what's happening if you burn something, so it combusts just on the surface, and laser-supported detonation. The detonation, because this wave leaves the surface supersonically in speed, at least in comparison with the surrounding atmosphere. In more detail, take a look at the pictures on the left, the laser-supported combustion, what in a one-dimensional case here for simplicity, and you see with the vaporization of material in the workpiece, which increases downwards here in these pictures, we get the formation of vapor, and the vapor moves towards the laser. It compresses the air in front of it, which forms a little shock wave, but this is a very weak shock wave, just transparent to the laser. So this process goes on and on. We may have some absorption in the plasma, but basically it transmits the energy or transforms the energy out of the plasma into the workpiece. In the LSD case, in the detonation case, it is different. We have the formation of vapor, and this vapor jet is so highly ionized that the electron density is so high that the absorption length of the material is so small that we get a very thin absorbing layer, and this absorbing state detaches from the surface. Of course, this laser heated plasma expands in both directions towards the laser and towards the workpiece. However, it is not fed by further energy on the back side of that wave, so it only is fed from the front side, and that's why it moves towards the laser into the direction of the laser incident direction. Here you can see a very schematically drawn picture of the situation. We have solid density at the workpiece, and during the formation of a plasma we get a decline of the density, orders of magnitudes in a few microns, extremely gradients in density, but that's enough to absorb laser radiation in this plasma by inverse Bremsstrahlung, and this is actually the state that we try to cultivate in laser welding or even in laser cutting. On the right you see the three regimes again. So we have the positive regime, in which we are above the vaporization threshold but below the detonation threshold ID. So we have combustion waves. If we are under the breakdown intensity, we just have vaporization. If we are over the detonation limit in intensity, then we have the formation of the laser-supported detonation waves. As an example, I would like to show you an application, the absorption inside a vapor capillary. You remember the movie that you saw, that was a welding process. If the intensity is correct, we get maybe an absorbing plasma, maybe the radiation is absorbed by multiple reflections in the keyhole. But in any case, we will have no detachment of the plasma, because that would lead to pressures and would exert the melt out of the pool. So that's not what we want. Here we work in the LSC regime or below. So, what did we learn? Three things. Number one, from a charge point of view, a plasma is very, very similar to a metal. Number two, there's a limit number, which is the plasma frequency, which defines whether the light will be reflected or transmitted and absorbed. And as an example, number three, if you think of welding, then you see immediately the consequence of the right tuning of the electron density, which is the only variable that determines the plasma frequency, in order to balance the incoming light with the vaporizing material in terms of an equilibrium, such that the electron density is just enough to absorb a little of the laser energy, not too much and not too small, just right.